All right, well, let's take a look at an example of a difference equation that has a little bit more of a real world context to it. And so the scenario here is we've got some sort of savings implement, a savings certificate that's worth $1,000 initially, and it accumulates 1% interest each month. What we'd like to do is set up a difference equation describing the value of the certificate over time. Now, let me remind you first of all, what was the form of the model that we've been using? We needed to know the initial value, and we needed to know this update formula, which gives us the next value of the state in terms of the current value plus some change. All right, and so what we're going to need to do first of all is identify the pieces of information that are in the problem and relate them to this sort of formulation. And the first thing that you'll notice is that we are given the initial value, right? We're told that we have $1,000 initially, and so A0 could be 1,000. And then we're also told that we get 1% interest. 1,000% would be nice. 1% interest each month. And what that means is that the change in A is going to be 1% of what we had at the beginning of the month. So in other words, we could say that delta A is going to be equal to 1% would be 0.01 times the value of A. Right? That's the change. Every month we get 1% of what we had as an added bonus, and we're going to use a plus sign there again because this is interest. We're not losing money. And so our formula could be written as AN plus 0.01 times AN, or if we wanted to simplify that just a little bit, we could write that as 1.01 AN on the right-hand side, where I've just factored out an AN. Okay, so there's our model. Let me put that information on the slide really quickly. And we can then use that to try to create predictions for what we think the value of this certificate is going to be in the future. Now, in this case, this is a banking context. There is no uncertainty, right? The interest rate is fixed. And so we don't have any, there's no error bars for these estimates. We can be very confident that we know exactly how much is going to be the savings certificate. But what we will see later on in the course is that when we try to model other sorts of problems, particularly those that come from disciplines like biology, we'll see that these rules are going to be estimates rather than being actually precise descriptions of exactly how the values change over time. Okay, so there's our formula. Now, if we have this formula written down, we can start to use it to make some estimates, and we can actually try to solve the problem in a couple of different ways. The first way is to just use our, well, by hand or using a calculator or a computer, we can just compute the values of the state of the system at various points in time. So remember, A was representing the value of our savings certificate. And so we would saw at step 0, we had a value of 1,000, and we can just continue to compute the values at time 1, 2, 3, and so on. Each time we're just multiplying the previous value by 1.01. And you could store those results in a table. You could draw a graph of those results, and any of those would qualify as examples of a numerical solution. They're giving us numbers that represent how the solution behaves. Now, that's not the only way to analyze these types of problems. Sometimes what we'd really like to know is what is the formula that allows us to directly compute the value for the state at some future time. Now notice, in a numerical solution, we have to compute the values of A1, 2, and 3 if we want to compute A4. But an analytical solution would be a formula that allows us to skip to A4 directly. And in this particular problem, you can actually write down a nice formula. You can show that the value of A after n months is going to be 1.01 raised to the n times 1,000. And so that's a little more useful. And then if we want to know what the value is going to be 100 months from now or 1,000 months from now, we can directly go there without having to compute all of the intermediate values or search through a table or something like that. All right. So how do you actually find an analytical solution like the one that we just discussed? Well, it takes a little bit of work to get there, but there's a couple of things that you can do. The first is it's helpful to first write out what the few terms are, what's A1, A2, and 3, in terms of A0, so that you can start to see what is the pattern here. Well, how does it look like they're changing? And a tip that I'll give you is sometimes instead of just multiplying out You know, if you have 1.01 times 1.01 times 1.01, write that as 1.01 cubed instead of actually computing that as a decimal, because it might make it a little easier to see the pattern. All right, once you've seen the pattern, you want to make a conjecture. And so this is actually called the method of conjecture, because we're making a hypothesis for what we think the pattern is, and that means we're going to need to write down a formula for the function. And hopefully, if it's a relatively simple difference equation, we'll be able to do that. What we're going to see is that for complicated difference equations, that's not even going to be an option. And so we won't always be able to use this approach. Okay? Once you've got your hypothesis, though, that's still just a hypothesis. We're not sure that that works. And so what we want to do then is prove that this formula will always work. And you can use a method called proof by induction. Proof by induction says the following. If I can show that my formula works for the first case, and I can show that whenever it works for one case, it's going to work for the next case, then we can show that the formula works for everything. So it's a little bit like dominoes. If you imagine, you have a stack of dominoes, and so imagine these vertical lines are all dominoes. If you can convince someone that the first domino is going to fall, and that anytime a domino falls, it will knock over the next one, then we can be confident that the whole stack of dominoes, the whole row rather, is going to fall over. So the first one will knock over the second one, and again, we've shown that, hopefully we will have shown that when one falls, it knocks over the next, and then the second one will knock over the third, and so on down the line. So what we need to prove then are two things. We need to prove what's called the base case, show that the formula works at one point. And then secondly, we need to prove the inductive case, which means that, again, when it works for n, the formula will give you the right answer for n plus 1. So let's give that a try and see if we can prove the formula from the previous example. All right, so we want to prove that this formula actually works for all of the values of this model. And so we'll start with the base case. Okay, we've got a formula. An is equal to 1.01 to the n times 1,000. And that's a hypothesis that was formulated based on the pattern. Well, before we get into the proof, let's quickly verify that that seems reasonable. A0 we said was 1,000. And then to get A1, notice what I would have to do is I would have to multiply A0 by 1.01. All right, and then if I wanted to get A2, I would get A1 times 1.01, which is just 1,000 times 1.01. That's the A1 part, and then times another factor of 1.01. And we could continue that process. A3 is going to be A2 times 1.01, which is 1,000 times 1.01 squared if I have just A2, but then I have another factor of 1.01, so now it's going to be cubed. And from there, you can make your conjecture that An is 1,000 times 1.01 raised to the n. Okay, so there's our conjecture. Now we want to prove the base case. Does that formula actually work? And so let's check. A0 should be 1,000, and if we plug into our formula, we get 1.01 raised to the 0. Well, raise anything to the 0 and you get 1, and so we do indeed get 1,000. And so we've taken care of our base case. Now we need to check our inductive case. All right, and so we'll assume An is equal to 1.01 to the n times 1,000, and that's for some particular n. And now we need to show that that same formula works for n plus 1. All right, let's do that. Well, we know from our model that An plus 1 is equal to 1.01 times An. Right, that was the model that says whenever you want to compute the next value, you have to multiply the previous value by 1.01. Well, let's plug in what our assumption was. So this is going to be 1.01 times, going up here, we had 1.01 to the n times 1,000. Correct? And at that point, notice we could simplify a little bit. We could group the 1.01 terms together, and now we have a total of n plus 1 of those factors. And so we've reduced it down to the formula that we were trying to prove. Okay? So we showed that if the formula works for n, then it will also work for n plus 1. Given that we know that it works for 0, that means it has to work for 1. And given that it now works for 1, it has to work for 2, and 3, and 4, and so on, which means this formula that we hypothesized at the top works for every value of n.